Hello again, YouTube. The last time we left it, we'd actually implemented a binary tree structure using a couple of definitions, and then we have an initialization function which actually populated that tree and set up all the pointers so that each of the characters that we are encoding was in this tree structure. Now, the purpose of this tree structure, this is quite a big initialization function, so I'll just minimize it. The purpose of this tree structure, this data structure, was so that we can translate from Morse code, or sorry, the characters A, B, C, D into the actual Morse code elements, dots and dashes, that make up those characters. So actually the previous video, we actually basically took our character string from the application and loaded it into a circular buffer for transmission. So we messed about with the circular buffer, then we messed about with the binary tree, but we haven't actually transmitted a character as yet, so we should really sort that out. So we'll create a function that would just transmit a character. And we'll create it static because it's going to be private to this file, and we'll stick a prototype up here to this function. So I have a simple function that transmits a character, and assuming we have that, we haven't at the minute, but assuming we have that, we should actually put in a check at the top of this transmit function that says the checks is the transmit buffer empty. And if the transmit buffer is empty, look, what this function is doing is loading up the buffer so that the characters are buffered until such a time as the transmitter is ready to transmit them. So they're in a queue waiting for the transmitter to be freed up, at which point the next character will be taken from that queue, from the buffer, and transmitted. So if the buffer is already empty, we don't really need to wait for the first character. So we should check that. So if there's nothing in that transmit buffer, we could actually transmit the first character that's been passed to us by the application layer. And we only want to transmit, like we tested here and only added valid characters to the transmit buffer, so we should only transmit potentially we should actually strip off, ignore all the characters at the start, all the letters at the start that aren't valid. And I think we'll remove a space, because at the end of a word, a space indicates, in the English language or whatever, a space indicates the end of a word, and the end of a word in Morse creates a silence on the line, or a period of no transmission for 7 periods. So at the end of a word, we're going to have silence for 7 periods, and there's no real point in adding another period of 7 at the start of the next word. So we'll just get rid of that part of a valid character. And if we actually reverse the logic of this and actually test for invalid characters, so if it's less than A and greater than Z, it's invalid, and we don't care about it. And we should actually just move to the next. Ignore that character, move to the next character. So if somebody tries to transmit the series %, ampersand, $, space, T, then we'll ignore those first characters, and the first thing we're going to transmit is the T character. And because we've transmitted the T character here, we should actually increment over that to the next character, so that that T character doesn't get added into the circular buffer and retransmitted. So now the next thing, just when I think about this, once a message is transmitted, once whatever character, the last character in the transmit buffer is transmitted, even though the elements are transmitted, there is still a period of silence after that. So there's that period of silence that I was talking about, the 7 periods of silence for the end of the word. So even though the transmit buffer is empty, and even when the last character has been taken out of the transmit buffer, the transmitter is still going to be transmitting the dots and dashes that made up that character. So just testing that the buffer count is 0 isn't enough. We should actually test the state of the transmitter and make sure that it's idle. So we have to have something representing the transmitter state, and if the current state is idle, then so there's nothing in the transmit buffer, the transmitter is currently idle, we'll just simply transmit the first character. So now we have to actually create this transmitter state functionality, and we'll do that in we'll just create an enumerated type. And one that we want is obviously idle. And we can be transmitting an element, and we can be transmitting a space. There's a couple of different space characters, and then we'll just create the variable that we wanted. So on that line, when the transmitter state is idle, and so we should at the bottom of this initialization function, after we've initialized all the binary tree stuff, we'll just initialize the transmitter state there. I'll just check, is this so? That seems sensible. If we then populate this, we have to now, in this transmit character, we're receiving an ASCII character, we have to use our binary tree that we've created. So if we're pointing at J, we have to work back up through the parent nodes to work out what the elements we need to transmit are. So we'll have two variables, two pointers into the various nodes in our binary tree. So we'll point the child at the character we've been passed. So if we got passed a J, the child pointer is pointing at this J node in the tree structure, and its parent is simply given by, sorry, it's a pointer, that parent element. So now we have to keep going back up the binary tree until we hit the top, and the parent of the root node, labeled start here, is going to be null. So then we'll pop out of this loop. So we now have to find out, is it a dot or a dash? So if we go to the parent of J, that's W. So now we simply have to work out whether J is on the dot or the dash child of W. Now we can easily see here that it's a dash, but in code we're just going to say if parent so if the child is the dot child, we have to add a dot element to our list of things to transmit in reverse order. Otherwise, we obviously have a dash element. And now we can actually move up to the next. So we go up to W, and now we go up to A, the next parent in the list. So if we set child equal to parent and parent equal to child parent, that's going to take us up to the next node in our binary tree, and we're going to come through this again. So now in this block of code we have to actually store a record of what. So we'll have to store dash 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 dot. So we need a structure to keep this information, and because we're only storing either a dash or a dot with two distinct values, we can just use a bit 0 or 1. So we'll say that a dot or a dash is either 0 or 1. We can sort out what their implementation is going to be, but we only need a bit for each of the elements. And because this tree structure is it's 6 deep right at the bottom here, and we're not even encoding these at present. We're only encoding down 4 layers, so we've got four elements to store. So we could actually store this into we could actually just store this in an 8-bit byte. So we'd have So we'll just take an 8-bit byte and use this as our storage mechanism for. So we've done quite complex data structures in a circular buffer and a binary tree, and we'll just say that 0 represents a dot and a 1 is a dash. And this is the elements that we have to transmit. So we'll call this elements. And we'll set up a variable called mask. And if we call that binary for the minute 0, 0, 0, 1. So that points at this first bit. And we'll load this up. So if I just do that in code, if we use the mask to load up this bit, and then we can shift it 1 character so that it becomes 0, 0, 1, 0, and then load up the next bit, and so on up the list sort of thing. We could actually simply store this in an 8-bit byte. So if we do the transmitter elements and our mask. And we'll load that byte with the elements that we have to transmit for a character. So we should actually initialize those in the bottom of our initialization function. So now we've said there's a convention that, if I go back down to our transmit character, we've said that the convention is a dash is 1. We should actually check coming into this, the mask. We should check the mask. And if it's not equal to 0, then there's some problem. I know we should actually we should code for that, and we'll do that in the future, but for the minute we'll just return. So the mask should be 0. If the mask isn't 0, then somebody's actually using the transmitter. That we shouldn't have got into this. So let's initialize the transmitter elements to 0, and we'll now load it up. So if it's a dash, we've said that we want to set the bit to 1, and we want to point at we've come in, the mask is 0, that's fine. We now want to set it to 1, so if I use binary, so if it's a dash, we want to say transmit elements is equal to, I'll do this longhand, we do want to do a bitwise OR of the current transmitter elements plus their mask. And that will set that bit. Now we've initialized the transmit elements to 0, so we don't actually have to do anything in the dot side, because we've initialized all these character or bits to 0. So we're just setting 1s as we encounter them. So the obvious thing we have to do at the end of this is shuffle or shift the mask element. I'll do this long-winded as well. So TX, and we want to shuffle it up 1 bit position, so it becomes 0010 and on up the line. And we can actually get rid of, because we're not actually doing anything for the dot, we only have to record dashes. So now, once we pop out of this, if we were doing a J, so it's dot dash dash dash, we would have we would have dash 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 dot, and then we would have incremented our mask, and our mask would be pointing at this bit. So we actually want to take it back down to this bit, because we've got to the end of the while loop, we've got to the root node of the binary tree, and we're no longer loading up the next bit in our elements field, byte, sorry. So we're no longer loading up, we want to actually go pop down, and this is where we want to transmit from. So we now know we've got to transmit from that point. So if we shift the actual so when we get to this point, we have a mask pointing where we want to transmit from. And we now have to start doing whatever it is we want to do for transmission. And now we get into another can of worms almost. If I just move quickly to the asynchronous function used a timer, which is, and this start timer, I'll just copy it for the minute. And there's a lot of stuff in here that we haven't coded, so we'll just get rid of it for the minute. But I will leave this at the bottom. So we've got a timer function. We also need Morse to turn on and how we did that in asynchronous was we basically set a latch, the port D latch we either set or cleared. So in the case of setting it on, if we just have this function to turn the channel on. So now we've got a problem insofar as if I try and build that, apart from the fact that those functions aren't used, we've got undeclared identifiers. This latch A and start timer, they're using hardware. Now we're using the DS pick 33, so if I could clear those errors with a hash include of xc.h. But one problem is that although it's cleared the errors, because I've included that file, our code is now hardware dependent. We're actually creating hardware specific code. And when we started this, we were basically, I tried to make an application independent module for Morse. In our examples that were synchronous and asynchronous, of examples of synchronous functions, asynchronous functions, we had application specific. So this function can only transmit THE, and if we have an application that requires THE, that's perfect, it works. But we were trying to make something which was more not application specific, whereby we had created an API function which could just accept a string of characters, and it didn't implement any kind of policy on the application. Now our application main.c or whatever we're writing can create whatever it wants. If we make this hardware dependent, it makes it much more difficult to it makes it much more difficult to test the code that we're writing. If I get rid of these two functions, now we have to, at this point in the code, we have to we obviously have to turn on the channel, the Morse channel, whatever that is. It could be a LED, it could be a speaker, it could be whatever, but we have to turn it on and we have to start a timer. If I get rid of these two functions and get rid of xc.h, all this code is platform independent. So at the present moment, it's not application specific. So it's independent of the application, and at this point it's independent of the hardware that we're running it on. So if I, for example, go to a terminal, I could use GCC to compile that file, and we've got Morse.0. So we've just compiled, even though we're writing this for a DS PIC33, this code is portable. It doesn't care at the minute. As soon as I add in that latch, if I add in that line that messes with an actual specific register in hardware, see, it's automatically, because I've added that line, it's added in the function that or the header for the processor we're using. And this now still builds on in our IDE for the PIC. But if I go back to compile that for my actual machine that I'm writing on, it's not going to have a chance. So how do we make this, or can we make this, and why would we want to make this platform hardware independent? Well, one of the reasons I'd suggest is that we can actually make this, it could be quite useful for something else if we want to run this on another piece of hardware. And there's a certain school of thought, I suppose, that suggests that you don't write features that you're possibly not going to need. So and maybe you're never going to, like, the argument would be you're never going to run it on a different platform. But if we make this platform independent, we can test this much easier. And the chances are we could use it. And to be honest, I think it creates better, more readable code if you are platform independent. So I think I'll leave it there for the minute, and we'll come back to this problem of we've got to turn on a channel and start a timer. And I'll think about how I'm going to do that, because I think we should actually leave Morse at the minute and address those issues before we go any further, and come back then to this module when we have a better understanding of that independence. And hopefully if we get that independence, we could actually compile this module into a Linux main.c and execute it. So we'll move away from the DS PIC and the cinnamon bun next time. I'll leave it there. Thanks a million for watching.